Hello 171 class, this is your notes for section 1.8 inverse functions. So what we want to do here is take these two functions, f of x and g of x, and we want to put g into f, and we also want to put f into g. Remember, that's what this notation means. So this is like from compositions at the end of 1.7. So remember, part A, putting a function in another function means to take all of the right hand side of this g function. This is how we get g, and we're going to put that in place of the x right here. We're going to replace x with all this. So I'm going to get 6 times all of this. So 6 times, I'm going to put a parentheses, x plus 3 over 6, and then minus 3. Alright, now, the 6's right here are going to cancel, and you're left with x plus 3 minus 3. And then the 3 and the minus 3 are going to cancel, and you're just left with x. So what we get here is f of g of x is equal to x. And then when we do b, now we're doing a reverse process here. So now we're going to take the right hand side of this function f, and we're going to replace it in to this g function where the x is. So we get, instead of x plus 3, we're going to have 6x minus 3 plus 3 into the numerator. And then we divide that by 6. And if you look, what's going to happen up here on top, the minus 3, the plus 3 cancel. We're left with 6x over 6, which is just x. And what we get here is that g of f of x is also equal to x. So remember what I said in the last section, that if they are the same, it's a special case. This is one of those special cases. This is, they're both given the same output, which they typically don't. But they do here, and they're both given x. So look what's going on. X is the input. We take the input, we put it into g, and then we take that output of x going into g and spit that into f, and what happens? It turns right back around and gives us what we started with. And then if we put x into f, and then do the stuff that f does, and then put it into g, we get right back to x, what we started with. So what I'm trying to say here is that f undoes the stuff that g does to the input, and g undoes the stuff that f does to the input. So make sure you understand what I'm saying here. Like, if I let x be 1, and I plug it in right here for this, I get 6 times 1 is 6 minus 3 is 3. So f of 1 equals 3. I mean, if I put 1 in, I get 3 out of f. Now take 3 and put it in where g is. So I plug in 3, the output of f, I plug it into the g function, and I get 3 plus 3 is 6. 6 divided by 6 is 1. I get right back to what I originally put into f. And that'll also work when you put things into g. Like, for instance, if I put 9 into the g function, or if I put a 9 in here, 9 plus 3 is 12. 12 divided by 6 is 2. So 9 goes into the g function, 2 comes out. Now take 2 and plug it into the f function. So I take the output of g and I plug it into f, and I get 6 times 2 is 12. 12 minus 3 is 9. And again, I get right back to what I started with originally. So they undo each other. They take away the operations that the other one does to the input. All right, ask yourself this also. What does f do to an input x? Well, it takes the input x and it multiplies it by 6. Okay, that's the first thing it does. multiplies by 6, and then it subtracts 3. Oops, 3. Now, think about this. If you were wanting to get rid of this, if you were wanting to undo what f does, what would you do? You would have to start with the last operation and undo it first. So the first thing you would do to undo it is to add 3. That'll get rid of the subtracting 3. And then if you want to, after you've done that, gotten rid of that, to get rid of the multiplication by 6, you would have to divide by 6. And if you look, that's exactly what G does. G adds 3 to the input first, and then it divides by 6. So the operations that F does to the input are undone by the operation that G does to an input, and vice versa. If this was your order of operations to undo this, if this is the second thing, the first thing you have to do is multiply by 6, and then you would subtract 3. So they are what we call inverses of one another. Alright, so what we just did on that last example is the definition of an inverse function. Okay, if two functions are inverses, then when you put one into the other, you always get back with what you started. Okay, inverse functions undo the operations of another function, okay, of their inverse. So you always get back with what your original input is. So that's how we test to know if two functions are inverses. We compose one into the other to determine that. Okay, there's the notation that we use. F with a little -1 as like a power. So it's read F inverse. So F of F inverse of X equals X, and F inverse of F of X equals X. Okay, now this is something that's really important too. Make sure you understand that. The domain of F, the domain of some function, is equal to the range of F inverse, and vice versa, meaning the range of F is equal to the domain of F inverse. Alright, that's important. You'll see that show up a lot with these some of these examples I'll give you. Alright, so to show two functions are inverses of one another, again, you're just being asked to plug G into F, F into G. Remember, this is the same notation as this. Okay, so don't worry about the different notation. They're both the same. Alright, so plug G into F. So take all of this and replace that X with it. So I'd have 4 times all of this, X plus 7 over 4 minus 7. So same thing's going to happen as last time. The 4's are going to cancel. I got X plus 7 minus 7. And then the plus 7 minus 7 cancel, and I'm left with just X. So there's half of it. Now you have to show both. So if I plug in F of X into G, so I'm replacing X, this X here with this, I end up with 4X minus 7 plus 7 over 4, okay? Again, all I'm doing is just taking this X and replacing it with this. So there's where the X was. I had a plus 7 after it divided by 4. So there's my 4X minus 7, replacing that X, and then there's the plus 7 over 4. Okay, so the minus 7 and plus 7 cancel. I'm left with 4X over 4, and that just equals X. So I've shown that they are inverses of one another because I've shown that they fit the definition of inverses. I plugged G into F, I got X. I plugged F into G, and I got X. Alright, now, how do you find an inverse? Meaning, like, if I'm not asked this, if I'm given this, how do I find this? And it's not just guess and check, there is a procedure. So, the first thing we do is, if you have function notation, you replace f of x with y. Okay, remember f of x and y are the same thing. And then you interchange x and y. Okay, so let me just show you down here as we go through this what all this means. So I'm going to replace this with y. And then to interchange x and y literally means change this to an x, change this to a y, and then solve for the new y. Go minus 7, so that's 2y equals x minus 7. And then divide by 2, divide by 2. So we end up with y equals x minus 7 over 2. Okay, x minus 7 over 2 once we cancel this out. Alright, so we've done that. We solved for y. And then replace y with f inverse. So get rid of that. Replace y with f inverse. And there's our function. There's our inverse function. Alright, and just remember, what does x do to an input? It doubles it, multiplies by 2, then adds 7. So the inverse would need to subtract 7 first and then divide by 2 instead of multiply by 2. Okay, so that is the inverse of that function. Alright, I know this is an inverse. This is a line. Okay, so I know that it's an inverse. When I get there, it is a function. Alright, but if for some reason you end up with like y equals plus or minus something here, then that means it doesn't have an inverse. Okay, you can't use this notation, f inverse x equals plus or minus, because it too is a function, and you can't have more than one output. So the plus and minus, remember, that's two. That's a positive and a negative for that particular value. Alright, so let's go through this procedure. Find the inverse here. So replace f of x with y. Interchange x and y. So change this y to an x. Change this x to y. Alright, and then solve for the new y. So I need to subtract 1. I got x minus 1 equals y cubed. Now I need to take the cube root to get rid of the cube. Alright, if I do it to the right, I have to do it to the left. So I end up with the cube root of x minus 1 equals y. Alright, so instead of y, I'm going to replace it with f inverse. So f inverse equals the cube root of x minus 1. Okay, make sure you extend your cube root over the 1, because if you don't, it's completely different. Alright, so there's there's replacing f of x with y, there's interchanging x and y, solving for the new y, and then replacing y with f inverse. Okay, that's that 4-step process right there. So get that down, make sure to pause it and practice that. Now let's see what happens if we try to do that with f of x equals x squared. So if I take the f of x notation and replace it with y, I get y equals x squared, and then switch x and y, I get x equals y squared. Now, to solve for y, instead of a cube root like we did in this problem, I need to take a square root. And what you have to remember is when you take a square root, here, you have to take into consideration that if I squared some number and got x, then this number over here, when I undo this, when I take the square root, this could have been positive or it could have been negative. So we get y equals plus or minus the square root of x. Okay, now let me just illustrate it for you. If I squared a number and got x, right, let's say x was 9. If I squared something and got 9, then that number that I squared, y, could have been the positive square root of 9. But it also could have been the negative square root of 9. Right? Because wouldn't that work? If I squared negative 3, wouldn't I also get 9? Okay, so we're getting two outputs for a given input, and that's not a function. And if you look right here, if the equation is not defined y as a function of x, and it doesn't, we're getting two y's for an x, the function f does not have an inverse, and the procedure ends. Okay, there is no inverse function for y equals x squared. Okay, it does not have an inverse function. Now you may think, well, doesn't y equals x, the square root of x, doesn't that undo squaring? Only if you start with a positive number. So this isn't a function, so that means that x squared doesn't have a inverse function on its entire domain. So we gotta keep in mind what step 3 is saying. That's what step 3 means by if we don't get a function there, we gotta stop. Alright, now if you think about this, y equals x cubed looks like this. And that did have an inverse. And then y equals x squared looks like this. And it does not have an inverse. So what we get from this is something called the horizontal line test. The horizontal line test says that if a horizontal line passes through the graph of a function more than once, then that function does not have an inverse. So a horizontal line would pass through y equals x squared twice. So y equals x squared does not have a function, but a horizontal line would never pass through y equals x cubed twice. So y equals x cubed, the example that we did before that, this one does have an inverse because it passes passes the horizontal line test. Y equals x squared, a parabola, fails the horizontal line test, so it does not have an inverse. Alright, so I'm going to just quickly stick a horizontal line in here. And then when we move it around, we see this one, a horizontal line would never hit it more than once. So all lines are going to pass a horizontal line test. So this one has an inverse. Obviously this is a parabola here, the next one, so it's not going to pass the horizontal line test. Okay, parabolas do not have inverses. Okay, this is a cubic, but it's a cubic that bends. It has that square component to it probably, so it fails the horizontal line test as well. So it does not have an inverse. And then the last one, again, it never hits more than once all the way through. So it passes the horizontal line test. So A and D has an inverse. And then B and C has no inverse. Alright, so failing the horizontal line test means there is no inverse function. Alright, now what we mean, if you notice these two graphs that do pass the horizontal line test and the graph that don't, what they do have in common is that they're always increasing. They're always getting higher and higher and higher. Right? They're always getting higher. They never loop. They never go from increasing to decreasing at any point, or decreasing to increasing. And that's going to be a characteristic of these functions that have inverse. They're always increasing, or they could possibly be always decreasing. Okay, if we flip that thing over, it would still pass the horizontal line test, but it would always be decreasing. So a function that passes the horizontal line test has to always be increasing or always be decreasing. And that's what we call a one-to-one function. Right? A one-to-one function is like a prerequisite for an inverse. All right, this is another interesting characteristic of an inverse function. A function and its inverse will always reflect over the line y equals x. They'll be perfectly mirrored over that line, meaning if a point AB is on the graph of some function f, then you flip B and A, which literally the x coordinate becomes the y coordinate, the y coordinate becomes the x coordinate. They flip over, and that point is on the graph of f inverse. Okay, that always will happen. All right, and from one point to the next, they'll intersect across a 90-degree perpendicular line to y equals x, which is an interesting property. But if you think about it, that step 2, when we were going over the steps to find an inverse, step 2 is interchange x and y. And that is the reason why we're seeing this. You interchange x and y, you literally switch x and y, and then we're seeing that process. And that's why we're reflected over the line y equals x. The y coordinate is the x coordinate. The x coordinate is the y coordinate. And they flip-flop, they've changed places, and we're getting that property of that reflection around there. Okay, but we're also seeing it right there. Interchange x and y. We literally do that when we come up with the graph of the inverse function. Alright, now using that property, if I'm told to graph both a function and its inverse, here's a function. This is x plus 1. Okay, remember x plus 1 looks like the square root function shifted one place to the left. Alright, now all I have to do here is take the points like negative 1, 0 and flip x and y, so that would be 0, negative 1. Alright, this is the point 0, 1. Alright, if I flip x and y, that would be 1, 0. This is a point 3, 2. If I flip x and y, that would be 2, 3. Alright, and you can see as I plot more and more points, I'm getting that symmetry over the line y equals x. Alright, 8. If I plug in 8, 8 plus 1 is 9. The square root of 9 is 3. So 8, 3. So that would be 3, 8. Alright, and then there's the points that would be on the graph of the inverse. So there's f of x and f inverse graphed on the same plane. And again, we see that symmetry over the line y equals x. And there's y equals x. That dashed line. Alright, so this is some homework examples. This is number 16 in your 1.8 homework. This is composite functions from a grid. So if you look, what this is saying is plug in 8 into g. So if 8 goes into the g function, we get out 2. Alright, and then that means now we're going to plug 2 into the f function. So 2 goes into the f function, we get out negative 4. Alright, so f of g of 8 is the same thing as f of 2, and f of 2 is negative 4, so f of g of 8 is negative 4. Okay, so this 2 that was the output in the g function becomes the input into the f function. Alright, and then similarly, same thing here, we're plugging 9 into the g function. So we're plugging 9 into the g function, we get out 4. Okay, so now this is f inverse, not f of 4, but f inverse of 4. Now, remember what f inverse of 4 means. If you plug the number into the f function, you get 4 out. So basically, what we're being asked to do here is, we know f of x is 4. And then we're being asked to find for what x. Is that true? Alright, so it's when we see f inverse of 4, we're looking under this column. So f of x is 4 when x is 0. So f inverse of 4 equals 0. Okay, so it's like we're flipping the roll around. So f inverse of g of 9 is 0. Okay, so 9 goes into g, we get out 4. 4 goes into the f inverse function. So from what we know from this table, 0 is what makes f of x 4. So f inverse of 4 is 0. Alright, and this is number 18 from your 1.8 homework. If this is the function, f of x equals 3x minus 7. That's f. We want to evaluate the inverse of f at 5 without finding the equation. Okay, So you could find the equation to find that, obviously, but if you're being told to do it without that, remember, what we're being asked to do here is figure out what x value makes 3x minus 7 equal 5, okay? It's like saying plug in, remember, f of x, if it was just f of 5, it means plug 5 in for x. F inverse of 5 means what value of x makes f of x 5. Okay, so it's completely different, that notation, from this inverse notation. So instead of plugging a 5 in for x, we're plugging a 5 in for f of x and solving for x. So we add 7 to both sides. 12 equals 3x. Divide both sides by 3, we get x equals 4. Right, and we divide by 3 right there. So x equals 4, so that means f inverse of 5 is equal to 4. Alright, now even though it says, don't find the equation for that, remember the process would be take y in place of f of x and then switch the x and the y. You can do this to check anyway. Alright, add 7 to both sides. And then divide both sides by 3. Alright, and we get f inverse is equal to x plus 7 divided by 3. Alright, and then to evaluate that at 5 just means now it does mean plug 5 in. So f inverse of 5 would be 5 plus 7, which is 12, divided by 3 is 4. And if you look, when we plugged in 5 here for f of x and solve, what did we do? We added 7, and then we divided by 3. Okay, so anyway, we ended up doing the same thing. Even if we did find the equation, we would end up doing the same thing. But just know that you don't have to actually find the equation to evaluate at a point. You just, instead of plugging in for x, now you plug that number in for all of f of x, and then just solve.